Today we're going to do section 3.2, the calculus of vector valued functions. Now first let's look at the derivative. What is the derivative of a vector function? Now a derivative is identical to what we did before, which is that famous limit that we beat around all the time in calculus 1. This is the exact same thing, where in here you notice that limit means you have three functions to think of, okay? Each component applies. So having said that, we're going to try one. Now look at example 3.4, where you have some random vector, and you're supposed to calculate the derivative of it based on that definition. So we're going to do exactly what we did before, except that now you have three components to take the limit off. See, there's a big long thing, and but do not get intimidated by it, because when you stare at it more closely, it's just three equations. There's the one with I, and the one with J, and the one with K, okay? And you manipulate all that stuff and do the basic limit derivative function to come up with some simple result in the end. So please do that as part of your homework, example 3.4. And then now that we went through that and realized that the limit calculation just means that you're going to take the derivative of each component, here's theorem 3.2, which makes life much easier. Okay? Instead of doing the limit, we're just going to take the derivative of each piece. Say if RT, look at part 2, okay? RT is, I don't know, some f of ti, g of t of j, ht of k. Then what is the derivative? Is you take the derivative of each component function, f prime of t, g prime of t, and so on. And that's all you have to do. So with that, please do example 3.5. The work is 3 times, but it's no different than what you did in calculus 1. So please do example 3.5 as part of your homework. Next, let's look at theorem 3.3. We have a bunch of derivative rules, and when you look at it, you can see that most of them follow exactly like the regular derivatives. Now that we're doing vector derivatives, there is no real difference. Except for all the products. You have to look at the products carefully. First, if you had a function being multiplied to a product, and you take the derivative of this product, okay, like part 3. Look at part 3 in your book. If you have a function multiplied by a derivative, you just apply the regular product rule as usual. Now, part 4, if you have a dot product, you still just apply the product rule as usual, which is first part times the derivative of the second plus second part times dot the derivative of the first. Here, times means dot, okay? And so that's all you have to do. Is actually no different. And what's more interesting, look at part 5. Even the cross product works the same way. You just take the derivative of one vector, cross the second one, and then plus the first one cross derivative of the second. That sort of thing. Of course, the cross product being, you cannot flip it around, so you have to do the derivative carefully. Don't flip anything around. You have to follow that rule of crossing. You know, you only do a cross. You can only cross first cross second, not second cross first. That would be the only difference. And then the chain rule applies as always. That the same way as any other the chain rule. So if you take the derivative of vector r that has a function in itself, then it becomes the vector times what's the derivative on the inside. Now part 7, I want to call your attention specifically to part 7, because it's an interesting theorem that will show up in the homework in a neat way. That is, if a vector dot is self equal to a constant, if a vector function dot is self equal to a constant, a vector always equal to a constant when it dots something, anything. I mean, dots some other vector, right? So if a vector function dot itself and happens to end up being a constant all the way through, then this vector dot its derivative will be equal to 0. Okay, that's just how it works out. Now, and next, let's look at the proof of this. Now the proof of this theorem are all straightforward. The way you prove it, for example, the dot product, the product rule for the dot product, well, you write out one side, write out the other side, and realize, hey, look, they're the same. So please do the entire proof, all the proof that you see here, okay? Please repeat all this proof for theorem 3.3 as part of your homework. So now I know that sounds tedious, but it's worth doing one time. And being that we are doing derivatives of the third degree, which is the same as the other degrees, but still it's a little bit new area, you know. So doing some of this grunt work is good for building confidence and abilities, that is efficiency, or well, anyway. So next, let's look at example proficiency. That's what I wanted to say. Proficiency. That way you feel like you're good at it by working with it a little bit to get a feel for this stuff. So some of the grunt work is necessary. So with that, let's look at example 3.6. And you're supposed to take the derivative of the dot product and the cross product. So please do that as part of your homework. That's all straightforward, tedious, but straightforward. Next, let's look at the next page, 275, the tangent vector. What is a tangent vector? A tangent vector is, you have a graph in space, okay, that's happily going around like that, right? Here's space. And then at some point, there's a vector that is tangent to your graph. That's your tangent vector, as you can imagine. Now, the tangent vector, as you can see, is given by the derivative at this point, as you can imagine, and that will be a tangent vector. The unit tangent vector is the derivative at this point divided by its own magnitude. That way it's called a unit because it has a length of 1. So that will be a unit tangent vector as given by your book here. So what you do is to find the unit tangent vector, you take the derivative and then divide it by how long that thing is at that point. So you get a length of 1. And this is called, your book called it the principal unit tangent vector. It doesn't really say why, I don't think, but it doesn't matter. It probably means that's the, I don't know, one of them, because you know that the other one is pointing the other way, okay? There's a negative version. So, but we'll just call it the unit tangent vector, which is what your book says. But do remember that there is a negative one that's also tangent to the graph, but it's going the other direction. Anyway, so let's look at how do you find the unit tangent vector? You take the derivative divided by its length. So that's how you will do example 3.7. Please do that as part of your homework. Next, let's look at page 276. We're done with taking derivatives. Guess what comes next? Integrals. Let's integrate all these vectors. How are we going to integrate some vector? As you can imagine, we'll integrate each component. And depending on whether it has a 2D vector with 2 components, 3D vector with 3 components, makes no difference. We'll integrate each one. And then whatever the result is, whether it's the definite or indefinite integral, we're going to pull that off and then come up with some kind of answer. That's all we're going to do. Now, you remember that in this case, when you integrate, let's say, a 2D vector, the indefinite integral, which has a c attached at the end, right? Well, in this case, our c is still there. Like, for example, check out this 2D integral. Now, we have an I and j, right? So you integrate each one. You have 2 constants, which is c1 and c2. What we're going to do is the c1 will be combined with I, right? And c2 will be combined with j. And then we'll call the c1i and c2j as a new vector, c, where it has components I and j. And c end up being any vector that will, basically the same way as in the 1D integration, the constant c is any constant will work. This becomes any constant vector will work for the integral. And this is an example for 2D integration. The 3D one is exactly the same. So remember that part. So that is when you do an indefinite integral of a vector function, you will have a constant c, just like the other previous times, except the c is not a number, it's a vector. Any vector will do. Now, having said that, let's look at example 3.8. As you can see, what that means is that now you're going to do integration not just because of one function, but of 3 functions at a time, which sounds like a headache, and it is. But it's good to put in some time and work through this stuff. Okay, it's just something that we have to do in Calculus 3. Remember, there's a difference between tedious and difficult. Tedious just means you have to drive 1,000 miles, 100 miles at a time. It takes forever, but everybody can do it. So please do example 3.8 as part of your homework. For homework to this section, please do problems on page 279, problems 43, 47, 53, 56, 61, 65, 73, 77, 99, 81, 85, 93, 95, and 101. And when you're finished with it, come back and I want to talk about some of the homework. Now that you're done with the homework, let's talk about problem 65. We're supposed to plot some somewhat complicated looking graph. So I plotted it in the Desmos calculator here, as you can see. Let me move it over. All right, take a look at what I got here. See, a beautiful graph that apparently comes out of the origin, and then you just type it in like that. And with there's not much to it. You type the whole function in with parentheses and commas to indicate 3 spots. And notice that the t goes from 0 to pi over 4, and that gives you the graph. Now, your graph might not look like it. Well, in fact, when I first graphed it, I couldn't even see it. So what happens when that happens, you have to adjust the axis range, so to speak. And that is, you can click the tools symbol on top right here. Let's see if you can see that. So if you click the tool symbol, anyway, so then this window pops out, and then it gives you, see, my x-axis goes from minus 300 to positive 300. So does the y-axis, whereas the z-axis only go up to like 8. Okay, because the thing just crossed very close to the ground, so you have to magnify the z-axis to see it close, to see it carefully. So that's that graph, and we're supposed to plot it. And then the next thing is, let's get out of here. The next question is, what happens when t approaches t approaches pi over 4, right? That was the question. What happens to the derivative? So I plotted the derivative here as well, as you can see here. I'll make it slightly bigger. All right, see, I plotted the derivative on here, and then so you can see the red line is the original function, and the blue line is the derivative. And as you can see, they look kind of the same. And also, this thing is going on, okay? It doesn't approach anything because the x-coordinate right here is has a secant. The y-coordinate also has a secant, so it's gonna get really, really big. So the answer is that it approaches infinity, and it's not gonna, that's where the derivative is gonna head for. And I think that's all there is to this problem. Next, let's look at problem 73. Problem 73, we are supposed to prove something called, if the vector function is constant, then it is always perpendicular to its derivative. Okay, and that orthogonal, that is the book that your book like to use. Now what I did is first I tried to write it out in 3 components. Look at the part I scratched out. I tried to write it in 3 components, and then the length is equal to some constant. You take the square root and all, and then here's the derivative, and you take the dot product. It got me a whole lot of nowhere or something. And then I remembered that we don't need to do that. Okay, what we need to do is basically quote theorem 3.3 part 7, which says that if r dot r equal to c, and then and what is r dot r? R, that is the magnitude squared, right? So if r dot r equals the constant, these are functions, r of t, and then r dot r prime equal to 0. That's that's theorem 3.37 on page 272, and that directly proves the problem. And you don't need to do anything else. So that goes to show you that some of the theorems in the vector calculus is very nice and handy. That marks the end of this section.